Morning students, welcome you all to this part 2 video on ARM instruction set. Hope you have gone through the part 1 video, okay, and hope you have understood, and most of you have given the correct answer for the review question that I have asked at the end of part 1 video. So now let's watch the part 2 video of ARM instruction set. In part 1 video we have seen about, so these are the total, there are totally 10 types of instructions: data movement, load and store instructions, arithmetic and logical instructions, multiply, long multiply, branch, flag related instructions, semaphore related swap instructions, multiply register data transfer instructions, or otherwise also known as stack instructions. Okay, and we have the 10th category, which are special instructions. So out of the 10 category, in part 1 video we have covered branch instruction, data movement, load and store, and arithmetic and logical instructions. Okay, so 4 of these instructions we have already seen very detailed explanation about it in the part 1 video. The remaining 6 types of instructions we will be discussing in this part 2 video. Okay, so let's go. The first category is multiply instructions. Now, in the processes that we had discussed earlier, that is 8085 or 8051, 8085 do not have a multiply instructions. You have to only do consecutive addition. But 8051 had a direct multiply instruction, so we just multiplied. But there was no speciality given for multiply instructions. It was one of the arithmetic, included as one of the arithmetic instructions. But in ARM, this multiply instruction is given some specialities because, ARM has a special block known as, multiply and accumulate, MAC. We have seen that during the architecture. So here multiplication happens in this block. Okay, so we'll see what are the 2 types of multiply instructions. We have 2 categories of multiply instructions. Please remember, this is known as ordinary multiplication. Okay, which means there should be a special multiplication also. Yes, that is the next type. So here, why the word ordinary means, so MUL means multiplication. Why the word ordinary multiplication here means, because you're aware that when you multiply 8-bit number with an 8-bit number, will the result be 8-bit or 16-bit? Yes, the result is going to be a 16-bit number, right? Similarly, if you multiply a 16-bit number with another 16-bit number, the result is going to be a 32-bit number. And if you multiply a 32-bit number with a 32-bit number, your result is going to be a 64-bit number, not again a 32-bit number. So, this multiplication, the result produced will only be a 32-bit number. It will not give you a 64-bit result. It will only give you a 32-bit result. Okay, so that is why the name ordinary multiplication is added here. So suppose you write MUL R0, R1, R2. R1 will be multiplied with R2, and the result of that multiplication will be stored in R0 register. So that is what will happen here. Okay, now a question may arise in all of you. Why is the result only 32-bit actually? Because here all data in ARM is 32. Then why should the result be 32? Only half of the result we are getting. Okay, is it a good type of an instruction? Yes, that's because ARM supports not only 32-bit data, it also supports 8-bit and 16-bit data. Especially when it's working in the thumb state mode, it will only be having a 16-bit data. So in that case, ordinary multiplication is enough. You can just use an ordinary multiplication where you will get 2 16-bit data multiplied, you will get a 32-bit result. Okay, so it is mainly used when you work with byte and half word data types. And the next is MLA, which means multiply and accumulate. So this, you have a special unit in the architecture called multiplier. So that part of the unit is used here. So when you write MLA R0, R1, R2, R3, what happens is R1 and R2 content will be multiplied. Okay, the center 2 registers will have the data to be multiplied. So R1 is multiplied with R2, and you know that whenever you perform multiplication, you have partial products, right? Even when you do multiplication, the paper and pen, you will have some partial products in between. So that partial products, each partial product is taken and stored after every step, okay, and then added back after the next step. So that is why you call it as multiply, and then you accumulate the partial product and add them. Okay, so this is like R1 and R2 is multiplied. R3 is initially 0. So it is added with R3. Then again R1 and R2 is multiplied, added with R3. Result stored in R3. Again R1, R2 multiplied, added with R3. Result stored in R3. So this continues. Suppose if it's a 32-bit number, this continues for every bit. Okay, and finally, once the final multiplication is done, it is added with the partial product in R3 and stored in R3. And then the final result is shifted to R0. Getting it? So this is like, every partial product is added, okay, then and there, and then the final result is available in R0. So now here the final result should be only 32-bit, not more than 32-bit result. Now, so these are the two types of multiplication which gives a 32-bit result, okay, MUL and MLA. Now, when you want the flags to be affected, if you just write MUL and MLA, the flags are not going to be affected. So you have to add a postfix of S in front of the instructions to make the flags to be affected. Say, for example, MULS. If you write it, then naturally the status flag will be affected. Okay, and you can also add any one of those 18 branch conditions. Okay, MULEQ, if I write, that means not that R1 and R2 should be equal, then only multiply. No, please don't interpret in that way. Whenever you add a branch condition, the branching has to be checked with the previous instruction. Suppose you have done a previous comparison between two values, and if that value is equal, then go for this multiplication. That is what is the meaning. Not this data has to be equal only, then it is multiplied. Whenever you add, I am repeating it once again, whenever you add those 18 branch conditions in an instruction, it will not check, the condition is not checked for that instruction. Condition is meant for the previous instruction, which is prior to that instruction. Got it? Please make this point very, very clear. Then only you will not have any confusion in the ARM instruction set. Okay. Yeah. So now this MUL and MLA can be used both for signed as well as unsigned numbers. There is no difference between signed ordinary multiplication and unsigned ordinary multiplication. Okay. Yeah. Now coming to the next type of multiplication is, we call it as long multiply instructions. Okay. So the word long here. So can you just guess what it means? Yes. The result can be a 64-bit result. Okay. So 64 cannot be stored in one register. So it has to be stored in two registers. So lower order of the result will be in one register. Higher order of the result will be in another register. So you take two register content, you will get the 64-bit result. Okay. So let's see what are the long multiply instructions. So MUL here means multiply, L means long, and U means unsigned multiplication. Similarly, MUL means multiply, L means long, S means signed long multiplication. Okay, so here ordinary multiplication only, but the result produced will be in two registers. Instead of taking it from one register, which is a 32-bit result, you will take it from two registers, which is a 32. So totally you will get a 64-bit result. And the number that are multiplied should be an unsigned number, which means you should not have a sign bit. MSB should not specify a sign bit. Okay, it is unsigned number. So here R0, R1, R2, R3, which means R2 and R3 are multiplied, and the result is stored in two registers, R0 and R1. So R0 will get the lower order 32 bits and R1 will get the higher order 32 bits of the result. Okay, hope this is clear. So that is the difference between long multiply and ordinary multiply. Similarly, this is for signed numbers. So same thing happens, but the two numbers are signed, then this instruction is executed. Now what happens is, if you have studied computer organization, you would understand this much better. So whenever you go for, the signed multiplication of numbers, actually there will be two separate algorithms. If the number is an unsigned number, it will follow a multiplication algorithm known as conventional algorithm. If it is a signed number, a separate algorithm known as Booth's algorithm will be used. So, entirely the algorithm itself, there is two paths. So if it's a multiplication, if it's unsigned, it will go to one path and follow conventional algorithm. If it is signed number, it will take another path and follow Booth's algorithm. So you have to specify in the instruction itself whether your data is unsigned data or signed data, so that it chooses with which path that it has to take. Okay, that's the only difference between these two. Now the next is MLA. So we saw that MUL and MLA are two multiply instructions. So similarly, MLA also goes for long, which means the result is a 64-bit result, and MLA for unsigned, and MLA is therefore signed also. Okay, so this is for MLA long for signed, MLA long for unsigned. Okay, so here what happens, R1, R2 and R3 are multiplied. Okay, and then the intermediate product results, that is the partial products, are stored in R0 and R1. So every time the partial product is added with it, and then the final product also is stored in R0 and R1. So you will get a 64-bit result here, where R0 will take the lower order 32-bit and R1 will take the higher order 32-bit. Clear? So here this is for unsigned. Similarly, you also have an option, same option for signed long multiplication. Okay, and accumulate. Now, similarly, the same rule applies, either I mention it or not. Whenever you add an S as a postfix, then the flags are affected. Okay, and similarly, you can also add any of those 18 branch conditions here, which means it will not check the condition of this instruction, it will check the condition of the previous instruction. Okay, I'm repeating this after every slide because it should go deep into your mind. Okay, and that is very important concept of ARM instructions. Now moving to a very interesting set of instructions which I personally like very much is stack instructions. Okay, and stack and semaphore instructions are something very unique to ARM and very interesting. Okay, let's see what it is. Now before going into the stack instructions, let me just give you a quick overview of what is a stack actually. So stack is a special kind of memory. You have a 4 GB memory in your ARM, right? In that 4 GB memory, a portion of the memory will be taken and used as stack. Okay, one part of the memory will be taken and used as a stack. So stack is a memory where first in, first out. Whatever you put, last in, first out. Whatever you put in last will be taken out first. LIFO, it works in the principle of LIFO, last in, first out. Okay, so what happens is stack has got two operations. One is push, another is pop. So push means you are adding data into stack. Pop means you are popping out a content from the stack. And you have a very important register related to stack, which is known as the stack pointer, right? Stack pointer. So stack pointer, what it will do is it will point to the top of the stack. So these are all some basic things about stack. So having known this, we will just see how pushing and popping happens in the next slide. Okay. So this is pushing data and this is popping out. One by one the data is popped out. Let's watch once again. So pushing, the first data is pushed, second, third, fourth. Now popping out, first data 7 is popped out, then 5, then 4, then 1. Got it? So last in, first out. So this is the two operations are push operation and pop operations. So pushing means putting a new data into stack, and popping means taking out data that is already existing in the stack. Now coming to this, we'll only consider push now. Now suppose I'm pushing a data into stack. See what all happens when I want to push a data. Just look at this animation carefully and tell me. There are two things that happens here. Okay, one is I'm pushing the data. Second, I'm incrementing the stack pointer. So this is the, let's assume this is a stack pointer value. Initially the stack pointer value was 3. Okay, now I'm incrementing it to 4. Now, depending on how this happens, okay, the way in which all this happens, the order in which all this happens, you can divide the stacks into 4 types. First, let me tell you, based on stack pointer, the way in which a stack pointer behaves, you can have 2 types of stack. In some stacks, stack pointer will be incremented to the next location. So if it was 3, it will move to 4. Okay, then if it is 4, it will move to 5, 6, so on. So that data will be added like this, ascending order. Okay, such a stack is known as ascending stack. So if stack pointer is incrementing, okay, and then data is pushed, then such a stack is known as ascending stack. The second category of stack, in some stacks, data will be added at the bottom. So as new data comes, it will be added here. Then another new data comes, it will be added here. Another new data, it will be added here. So what happens is, the data will be added to the bottom. Okay, so which means your stack pointer should not increment, it should decrement for getting a new data whenever a new data is pushed. Such a stack is known as descending stack. So it is up to the processor to decide whether you want an ascending stack or you want a descending stack. Okay, so that is two category. Now, as I told you, these are two operations. One is pushing the data, second is incrementing or decrementing the stack pointer. Now, the order in which these two operations happen, depending on that, you have two types of stack again. Suppose if your stack pointer is either incremented or decremented first and then data is pushed. I'm repeating once again. If stack pointer is incremented or decremented first, then a data is pushed. Such a stack is known as full stack. Getting it? The order in which these two operations happen. So naturally, what will be the second order? The stack is first pushed, then stack pointer is incremented or decremented. Okay, that is known as empty stack. Now you have four types of stack: ascending stack, descending stack, full stack, empty stack. In ascending stack, stack pointer is always incremented whenever you want to push a new data. In descending stack, stack pointer is always decremented when you want to push a new data. And in full stack, first increment happens, increment or decrement, anything can happen. First stack pointer changes, then data is pushed. That is full stack. In empty stack, first data is pushed, then stack pointer is either incremented or decremented. Now you may wonder what is the difference between this full stack and empty stack. I don't know if you remember, what is the reset value of stack pointer in 8051? It was 007, you remember? Not 000. It was 7. 7 was the initial value for stack pointer on reset, right? Why is that so? Because now see here the stack, suppose your stack is empty. So stack pointer is pointing to 0. Okay, suppose you have a full stack. What happens? First you increment the stack pointer, then you add the data. So what happens? You start to add the data only from location 1. So your 0th location will never get its data. It will always remain empty. You're getting it? That is the disadvantage if you use a full stack. But when you use an empty stack, first data is pushed. That means it will sit here in the 0th location. Then stack pointer is incremented. Then next data is pushed. Then stack pointer is incremented. Next data pushed, stack pointer incremented. So when you follow this process, you don't have anything empty. Okay, all locations are occupied. That is the advantage of having an empty stack over a full stack. Hope this is clear to all of you. So now, please remember these four words: ascending, descending, full, empty. Okay, now we'll move on to the instructions. So ST here means store. LD means load. Okay, now we are not using the word push and pop here, but instead store and load. So store is equal to push. I'm storing register content into stack. Okay, so into stack is push. And load means pop. I'm taking out a content from the stack to a register. So that is equal to pop. So store means push, load means pop. Clear with those two first letters? So ST means store, LD means load. Now what is this M here stands for? Multiple push and multiple pop. So suppose I want to push two register contents. If I write two instructions, first instruction will be fetched, decoded, executed, then one data will be pushed. Second instruction will be fetched, decoded, executed, second register content will be pushed. So see the time that is taken is too long, right? For fetching one cycle, for decoding one cycle, execution one cycle. So 3 cycles. Then again another 3 cycles for the next register content to be pushed. But ARM allows you for multiple pushing. So take one instruction, and suppose you say that I want to push R0 to R4. So R0, R1, R2, R3, R4. 5 register content is pushed in just one instruction. So you fetch only once, you decode, and then you push. So when you push, all 5 register contents are pushed in one go. Okay, so that is the meaning of this M here. M stands for multiple push. Okay, and you can decide how many you want to push. Suppose you say R0 to R2. So R0, R1, R2 will be pushed. R0 to R5. R0, R1, R2, R3, R4, R5 will be pushed. Suppose you want to push, certain registers, not continuously. So you can say R0, comma, R3, comma, R7. So R0, R3, R7 will be pushed. This is something similar to how you give this print option in when you're printing. If you want continuous pages, you give this to this. If you want discrete pages, you give comma and then. So similarly, you can also use here. And this F stands for, anybody? Full stack. Fantastic. And A stands for ascending. So we have seen what it is in the previous slide. Ascending, full stack. So you can have any type of stack. You can have an ascending stack, that means A. You can also have descending stack, that means D. You can have a full stack, which is F. You can have an empty stack, which is E. Okay. So store, which is push multiple times into a full stack, which is having an ascending type. Clear? So that is the meaning or interpretation of this instruction. So here all these 5 data are pushed, and please see here there is one more that you have to write, from which you have to start pushing. So your stack pointer has to be mentioned here. There are 2 ways of writing this. One, you can write SP, another you can write R13. Please remember, R13 is dedicatedly used only as a stack pointer. So here instead of writing SP, you can also write R13. That is also the same meaning. In some books, they would have even written STMFA R13, comma, within this curly braces R0 to R4. Okay, that means push all this starting from R13. Clear? So that's it. So here same thing, but your type of stack is different. Instead of full, you are using empty and same ascending. Here it is full, descending. Here it is empty, descending. Okay, so if you understand what is ascending, descending, full and empty, these instructions are very, very easy for you to remember. Okay, so this is post increment, pre decrement, post decrement, and pre increment. I hope you understand, right? So pre increment means you first increment, then you push. Post increment means first you push, then you increment. Okay, so pre decrement means first you decrement, then you push. Here post decrement means you push, then you decrement. Okay, so that is the meaning. Similarly, for popping also you have load. Instead of store, just use the word load. Okay, so just these 2 alphabets will change. So same as post decrement pop, pre decrement pop, post increment pop, and pre increment pop. Hope this is clear to all of you. So instead of SP, you can also use R13 here. Okay, so it's very simple. First look, it may be very confusing, but once you understand the concept of stack, it is very, very easy to understand what it is. Hope this is clear. Yeah. Now you have just 2 flag related instructions. Okay, majorly 2. Let's see what it is. So one is pushing the register content into CPSR. Okay, another is pushing the register content into SPSR. Okay, so MRS means you're transferring the content from from CPSR you're moving it into RD. From SPSR you're moving it into any one of the destination register. Okay, it can be anything. So suppose you write MRS R0, SPSR. From SPSR you're taking it and loading it into R0. Similarly, from CPSR you're taking it and loading it into R0. The next should be the opposite of it. When you write MRS CPSR R0, that means from R0 you're putting it into CPSR. Okay, this is whenever you get an interrupt, you have to store the register contents. So you can push it into CPSR or SPSR, whatever. But when you use these instructions, you cannot use these SPSR instructions when you are in 2 modes. Can you guess what are the 2 modes? User mode and system mode. Okay, when you are in user mode or system mode, you are not allowed to use the SPSR instructions. If you use, you will get an abort error. Okay, because SPSR is not available in the user mode or system mode. Clear? Yeah, so that is about flag related instructions. Next is semaphore related swap instructions. Now, before going into this, let me just quickly, with an analogy, explain to you what is the semaphore, because it's a new word for us. We haven't seen this word so far. So, what is the semaphore? We'll just see. Suppose you imagine a situation where you go into a library. Okay, there are 10 reading rooms. The reading room is a room where only one person can go in, sit inside, and calmly just read a book and come out. So there are 10 reading rooms. There is one person sitting outside to keep a watch of these reading rooms, whether they become empty, occupied, and all that, and so that he directs whenever a new person comes in. Now suppose 5 rooms are occupied and 5 rooms are empty. Now a new person is just walking in. He goes to this person who's sitting in front. Let's call he's a clerk. He goes to the clerk and asks, "Can I take one reading room?" Immediately he allocates one empty room, and then he adds one data to the occupied room. So occupied room now becomes 6, and empty room now becomes 4. Okay. So now he is directed to one room. He goes, sits, reads, and then comes. Now one person completes reading. So he has to come to the clerk and say, "See, I've done my reading. I'm going out." So immediately 6 was the occupied room. Now he'll minus 1, and number of occupied room will become 5. Okay. And empty room also will be updated. It will become 5. So this person who's sitting in front is similar to something known as a semaphore. So there are different types of semaphores. This semaphore that I have spoken about is counting semaphore. So what does this person do? If he is not there, simply somebody will walk in. Okay, they will occupy a room. They'll just walk out. So you don't know how many rooms are occupied, how many rooms are full, whether there is any empty room available. Nothing is known to you. Suppose all 10 rooms are occupied. Another 11th person is walking out, coming in new. He wants a room. He goes to this person and asks for a room. He says, "Please wait. All 10 rooms are occupied." Now somebody leaves. Immediately he updates the empty room, and then he calls him and says, "Please occupy this room." Okay. So there is a kind of a proper resource allocation of data, allocation of registers. So this semaphore concept is used whenever you go for multi-processors. That is, you have one core processor and you have many co-processors. Okay, so the job of the ARM processor is like task master. It will allocate tasks. Suppose any big mathematical operation comes, it will pass on the task to math coprocessor. Then maths calculations will be done. Something related to graphics or something, another new coprocessor with graphics, it will be just translated. It will take. So when many coprocessors are attached, there is a it's like 10 people trying to use those rooms. So everybody wants the room at the same time, or nobody wants the room. So somebody should be there to keep a note of what are the resources that are empty, what are the resources that are being used, and all that, so that this allocation doesn't have any confusion. So we have a concept called semaphores. Hope this is clear to you. So that, based on that, we have a few instructions. Let's see what it is. So one is read full semaphore. Okay, so here you can see SWP means swap actually. SWP R0, R1, R2. Now R2 will have, R2 is actually the semaphore value. So when it is given within brackets, it's an address, right? So R2 will have an address content. If you go and see in that address, you will have a content. So that is taken and loaded into R0. But after loading, your semaphore will have to be updated. So R1 will be taken and put into R2. You're getting? So a new person is coming in. He is allocated this room. And then the number of occupied room has to be updated, right? So this R1 will be stored back into R2. Okay, I'm repeating once again. R2 will be having a data, the address, actually an address semaphore. Go to that address, there will be a data. Take the data and put it into R0. So R0 gets the data pointed by R2. So R2 here is the semaphore actually. Okay. Then you cannot just like that copy a data and come out. You have to update. Okay, the semaphore. So that updated value is something but R1. So R1 will be stored at the very location pointed by R2. So will become the new value. So 5 rooms are already occupied. Another new person is coming now. That is R0. He wants a room. So you give him a room. Now 5 becomes 6. You're getting it? So now R2 was earlier 5. Now it has become 6. So that 6 is there in R1. Prida? So after taking R2 value, your R1 value is pushed back into the semaphore. Okay, so that is the concept of semaphore swap instruction. So this is for reading the full semaphore, you use SWP. When you want to read only a byte, okay, not the entire semaphore. For example, R2 will be a 32-bit address. So when you go into that address, you will take 4 immediate locations. So suppose R2 is 2, 2, 3, 4, 5. All the data will be taken. But here 2 means only 2. It will not take 3, 4, 5 and all that. Okay, because only 8 bits are needed. So this is, you can also read a byte. Instead of reading the whole semaphore, you can also read a byte. So this is swap full semaphore. This is swapping only the byte of the semaphore. Okay, so this is used for mutual exclusion. Whenever you have a multi-processor system, you have only one processor, this instruction is not used at all. Okay, whenever you have 2 or more processors, then for accessing data and all that simultaneously, so that there is no confusion, you go for these swap instructions. Clear? Yeah, and the last 2 instructions is special instructions. We have just 2 special instructions. One is called software interrupt. I think I mentioned this in my earlier video also. So whenever you want to invoke supervisor mode, okay, you want to shift to supervisor mode, you use an instruction called SWI. Okay, and followed by SWI, you should give a 24-bit immediate value. That 24-bit immediate value should tell you which portion of the operating system or which function of the operating system you need to invoke. You cannot go for the entire operating system. Okay, so one portion of the operating system you want to invoke. So you have to mention that as a 24-bit immediate value. And another interesting concept in ARM is breakpoint. So this breakpoint is nothing but, suppose you have a 10,000 code long program. Okay, you're writing the entire code, you're typing out the entire code, and then you're saving it, and then you're executing. Then you find 100 errors are there in the code. So that would be a big headache to solve all the errors. So what you do is, suppose you have a 10,000 big code. After every 500 lines of code, you add a breakpoint. Next 500 codes, you add one more breakpoint to it. The third 500 block, you add one breakpoint. So what happens is, whenever you add a breakpoint, that 500 alone will be checked, debugged for any error, and if there is any error within that block, it will be solved. So this is like divide and conquer. Instead of writing the whole program and then executing and finding out the errors, you insert breakpoints in between, so that that block alone is checked for errors, and then you solve it. So this is one way of debugging a program, by inserting breakpoints. Okay, so that instruction is BKPT. Clear? So this is all about ARM instruction set. Hope you enjoyed listening to this ARM instruction set. So you have very interesting instructions in ARM 7. So that is it. If you have any doubts regarding this, please, you can post it in the Google Classroom, or even you can give me a individual text message in WhatsApp. I would be very glad to clear that for you. And this is the last video on ARM processor series, ARM 7 series. Okay, thank you.